We have certain actions defined. These actions are defined in a particular way for use in a context-sensitive, like search within the game. That's a fancy way of saying that we're basically doing like a behavior tree-like structure for the dumb AI that's within the Unity game on the Unity side. So I'm going to explain some of the motivation for that and how this kind of translates to that. Why don't I open something else this way? So to give you guys a basic idea, this thing we're going to call the embodiment server. Embodiment is principally going to talk to a few components within OpenCog, like the perception action interface and OpenSide. I'll explain that in a second. And then it's going to communicate with the robot embodiment and say a game world embodiment. Maybe more in the future. So in this case, I'm showing you guys kind of what we set up with the game world itself. But really what it all comes down to, if you're designing, say, a mind agent in OpenCog, you'll be communicating with OpenSide, the perception action interface, and the embodiment server to have actions executed in the Unity game world. And we want to make this transparent and useful for you guys. So one of the ways we're going to do that is by setting it up in a kind of a hierarchical structure. So let's say that you just want to do something simple like a move command. We'll put this on the OpenCog side. And then on the Unity side, we know that this high-level move command, right, from like, you know, X, Y, Z to like, you know, X prime, Y prime, Z prime. On Unity, this is going to involve multiple actions, right? Because move might include like a forward move, right? Maybe you have to turn as well as part of that. So like, I don't know, turn left. And you have to animate all these as well. So if you want to specify a high-level action like just moving from one location to another, we don't want you to have to deal with the intricacies of manipulating the Unity game world, specifying exactly which actions it will take to achieve that goal and which effects, like animation effects, to do that. So the move action here actually corresponds to a behavior tree. So, for example, we have goal-directed behavior trees set up at each level, and that's what I'm showing over on the screen here. This is the behavior tree for the robot behavior at a high level. What it says is that this is a selector. It will select one of the following actions on each iteration of the tree. It will default to the left side first, and then it will move its way over towards the right. The show action is like the action that plays the idle animations. So by default, if it doesn't have a goal or anything else, it will just show. If it wants to say something, like it's hungry and it wants to find a battery, it will tell you that next. Then we move to moving, creating blocks, destroying blocks, and transferring blocks, which isn't implemented yet. So each level of the tree is goal-oriented. So what I mean by that is that each one specifies like a more specific goal as you move down the tree. So this is the move tree. The one, it's hard to see, but all the way on the left, forward move, up move, turn left, right, moving left and right, like strafing, moving backward or down. Right? If we look into forward move, we can see that this is further split in different types of movement, like flying, running, walking, climbing, jumping, and falling. So what you could do is you could specify on OpenCog side like more specific directions. Like you could give a list of like particular things that you wanted to do. So if you wanted to like it to be a walk, forward move, followed by a jump, left, move, followed by we'll just say a destroy, and a show happy, right? You can specify an exact list of the exact like lowest level actions that you want to expose, right? That will come from, again, the embodiment server. So in this case, right now we're using Shenhua's planner to actually set up plans like that. So I'll just put planner here. We're going to move to a better planner very soon, but for now we're using Shenhua's planner. And this gets more important as you start talking about the robot embodiment. Because for the robot, and what Hansen set up, things like walk, forward, move are still very high-level actions, right? Moving individual servos, right, is kind of the level of abstraction that they currently have exposed in the Hansen robot kind of robots. So our current plan, what we're hashing out, is to make maybe like a 5 or 6 level hierarchy of like action granularity, so that you can specify a goal for each, say, for example, particular limb of the robot to try to achieve at a given time. There's somewhat better ways to do this without behavior trees, but we found that behavior trees provide a lot of context-sensitive understanding that works well in the game world. So I'm going to load up the game world for a second again and show you a bit of what I mean by that. So this is a test level that we built using MCEdit, loaded in directly from the Minecraft format. This is the house that we set up for the character. The little earth is right there. And we put a TNT block to start right up here. And made this big tall tower that we wanted the planner to figure out how to fit at the top of. There's another gold block at the top of that. So to give you an idea of what I was talking about with the other stuff, I'm going to go over and I'm going to delete the TNT block and I'm going to put a bookcase right there. And what little girl doesn't want books? So she's going to run over and try and grab that. So she decides that she wants to do it.
Yeah, she wants the books.
Yeah, so right now we've set the books to be her goal block that she's going to move towards. So she's going to execute actions to move towards it. We're not, right now we're limited to creating blocks as goals, but we're going to change that in the near future. Theoretically, any type of action that could help her to achieve her goal is going to be available for her to use. It's kind of teleporting with it now. Then she destroys the block and she achieved her goal. So that's pretty straightforward. What I wanted to explain to you guys is that basically all of that movement and all of that maneuvering right there was done completely without OpenCog. That's basically just the behavior tree working a greedy algorithm to find the books and get there. That also didn't use any A-star pathfinding. It's pretty much as basic of an AI algorithm as you can get that still is able to do more or less complex actions. So now we've placed a goal block that's really up high at the top of this tower. She'll start, oh wait, I forgot, there's a problem in the jump down behavior right now. I have to help her down.
Why does she occasionally stop and look around?
That's a bug. It's basically the way I built the behavior tree right now. There's still moments where she's caught between animations where she chooses to idle. Her look around is the idle animation fire. So she's decided this is a good place to start building blocks. So she's going to start climbing up these ice blocks, and or diamond blocks, I guess, and try to get to the top. Because this isn't very smart, for example, she doesn't do any A-star pathfinding to figure out, oh, wait a minute, I can just traverse this staircase and get to the top. Instead, she chooses the most direct and most obvious path to get to the goal. I'm going to stop that because it'll take her a while. We were hoping to use that testing for the world. It turns out that it's a little bit too big for OpenCog to handle right now. So instead, sorry, I forgot. So here's the little girl again. This small level is just 256 blocks. Pretty easy to maneuver around it. So if we make a lot of blocks, she'll just keep going to the nearest one and try and do it. Now, if I go into VMware here, I always try to close the embodiment server before I restart it again, and I try to make sure to wait to see that it's working again. So that's what you should see, at least in the current version of the embodiment server. So I'm going to create a battery block, or a standard battery block right now, and I'm going to load the AGI robot. Since we saw that stuff appeared on the screen in the bottom right, all of his open size states, we know that it's working. We also can keep the command prompt open to make sure that things are working. You can see that he found a battery and that he's trying to figure out a way to go towards it. Sorry, I don't know why it stopped. Probably because I had deep learning. crashed. So restart that. And get back to it. I wanted to ask, well, we got a second here. First of all, does anybody have any questions about this or comments about this? Would you prefer it done a different way for any of the work that you're thinking about, or if you had an ideal test framework, how would it be?
Can you clarify again what you said is the main difference when you start using a robot?
When you start using a robot, the hierarchy goes deeper. Like for example, we have this thing walk forward move. That's because like it's moved forward and then walk at the bottom level, right? But for the robot, we're not restricted to the canned animations that we use, say, in the Unity game world. We can do anything the servos can do. And so we might have a, say, a more specific thing, which is like stiff knee, and a more specific one underneath that, which is like drag foot. So what is a drag foot, stiff knee, walk forward move? It's basically a limping walk, right? You might be able to construct a new high-level action for that later. Like maybe we just like turn this into a limp action or something, right? But the point being that these might not be the best examples, but you would have lower level actions that might be down to the individual joint movements, which are goal directed and are smaller than like whole level canned animation, because it's not until like we get 3 levels deep here that we actually have a canned animation ready. So I guess part of it is that, especially for problems like inverse kinematics problems, where you want it to reach out and grab a particular object on a table, like this, you want to be able to specify how each individual servo moves to connect the hand to the object you're trying to pick up. Because you're likely not going to have a particular animation that moves your hand in the perfect way to grab the item. So that's a part of it, certainly. The server started looking at this. So the green is the start location, the red is the goal location for this step of the plan. When he switches steps in the plan, then he finds it and he finishes it. I don't know what his next plan is, but so we're going to look at the console output to see kind of what was happening throughout the way there. So here, this is where it really indicates that we received a plan. As you can see, we're basically sending the plans and their individual actions through XML right now. So we're just serializing the plan to XML from embodiment and sending that to the game world. Plans can have a number of steps. This particular plan had 12 steps. And this was just the first part of a multi-stage plan, where the first stage was to walk up next to the battery, the next one was to grab the battery, and the third one was to consume it or destroy it. And so there's a lot more output in this console window from the editor than there is in the inside console window. You can see that this just shows some basics of, we received a plan, jump toward. We decided not to jump toward ultimately, but to just walk and run there, and then to grab and eat that battery. So, restart it. There. So in this case, because there's no batteries in the world, basically he can see his home, he feels safe, but he's hungry, and he's going to keep telling us that until he ultimately finds a battery. This action has the goal of this end location, or the start and the end location in the same place, which is why he's sparkling green and red. Oh, that's right. It's just going to keep timing out. So,
Do you know why the happiness and solitary emotions go a little bit back and forth?
That was based on some algorithm in the OpenCog that I'm not quite sure about. But if you read up some of the literature on the OpenCog stuff, you can probably figure out what's going on there. That's basically the bulk of what I wanted to show you guys, how it's set up right now. And I wanted to turn the focus a bit more to developments in the future and how we could set it up. So, I've explained how we set up this hierarchy of actions to sort of work its way down, and how that's sort of built using a behavior tree on the Unity side, but it should be implemented through something like an HDM planner on the OpenCog side. Would you guys, what's like other functionality or another way that we could have done that? Would you guys have wanted it to be very pedantic, like everything in the planner to specify each individual action that the character takes?
Perhaps it should be possible. Like you can specify a very high level action and have Unity worry about how to execute the whole plan. But if you wanted to, you could have more fine-grained control maybe.
Yeah. Well, we did set it up so that you can still have some more fine-grained control by sending it an explicit list. But right now, the limitation of this is that it has to know what these actions are ahead of time. And we wanted actions to be more discoverable, for example. Like, for example, if we didn't specify that this is the link action, right? And we wanted to figure that out through talking to people and them saying, hey, you have a link or something, right? Then we wouldn't want this to be specified quite so explicitly. It's fairly object-oriented right now. I mean, you can see how if we expand the girl out, you can can see, like, for example, hold right hand create is an action with two effects, an animation effect, which causes her to animate, and a create block effect, which creates the block. So that's kind of straightforward. For each action, we can specify a set of preconditions. Like in this case, we can see that she has to be on the ground. There has to be a path open for her to create an empty block. The end target that she's trying to reach has to be in front of her, above the climb angle, and she can't be running. She can't be running this action already, and she can't be running other actions. Okay. Let's see here. So, I'll put it to you guys. Would you guys want to see something like an implementation of the say action or the tell action so that it actually creates an effect on the screen? Or would you want to try to dig into some of the non-AI related stuff in the Unity engine that we built? Or would you just prefer me to spend some time and try and put these players up so that you guys can get access to this paper?
What do you mean about the say action? What were you saying?
So you saw that we were getting from the planner, it was telling us to say certain things, but like the character wasn't animating, they weren't really doing much. We could implement that so you guys could see how an action ends up being implemented in the behavior tree and stuff like that.
Oh, it's pretty straightforward.
It's fairly straightforward. It's not something that we necessarily expect you guys to do, but if you do end up contributing to OpenCog and you're interested in Unity stuff at all, we try to make it as easy as possible. If you guys do feel like you want to focus on the OpenCog stuff, you can always just ping me and tell me, hey, I want this feature in the game world. And I'm willing to do that. Why not put my email address back up so that everybody can see?
It might be interesting to hear about how it represents the world in the Atom space.
Okay. So right now, there's a thing called the 3D space map. Which is another component which hooks up to the planner and to the perception action interface. So the 3D space map, well, I'll say first, the order of operations is kind of like, we load the Unity game world, embodiment, we connect to embodiment. Embodiment sees that we haven't set up most of OpenCog to have received the atoms in its atom space, so it talks to the perception action interface to perceive the world's like terrain and other objects. After it perceives the terrain and other objects, that is put into the 3D space map, where it's then pushed into the atom space deeper in OpenCog. Now, the representation, as far as I know, is that there's basically like links between, I wouldn't say every single, well, let me correct this one. So sometimes, I think the way it's being done now is that we are actually pushing the 3D space maps data into the atom space. But in some cases, you can do that for like data which is very particular to, say, for example, a game world. If we have this 3D space map data and only, say, a few blocks are very important, or only a few objects are very important, only those objects or blocks will actually go to the atom space. The other ones will just be kept in sort of this private memory store. This isn't ideal because, of course, we want all of our knowledge representation to be in the atom space. I was just mentioning, Ben, they were asking about the representation of the world in the atom space. So, did you and Xuxing decide that you were going to push the whole 3D space map into the atom space, or just parts of it?
That's imprecise. What do you mean by push into?
Were you gonna? She was working on all the above, below relations and stuff. Did you guys end up sending that to the atom space in that representation, or just keeping it in the 3D
Well,
space?
I mean, in many cases, you will need those relations in the atom space. However, you don't need the full list. Like say near, there's a lot of things near other things, right? So the space map in principle, given a map of this room, could detect that each chair is near the chairs near it, each chair is near the table in front of it, and so forth. It is not necessary to export every single near relationship into the atom space. I mean, those are kind of implicit in the 3D representation, right? So it's kind of a control question, like which relations do you export when? So, for example, one reasonable heuristic would be the atoms which have a high short-term importance and are linked into the 3D space map. Then the spatial relations involving those things would be exported. So if she was very important in my atom space and she's near the chair, she's near the table, she's near the floor, she's on the chair. But if he is completely insignificant to me, then I will not record any of those relationships in the atom space. But they'll be there in the 3D space map. So if I later realize that he's like the world's first trillionaire, then all of a sudden these things will get exported into my atom space, and they'll pay a lot of attention.
All right.
So currently does every block in the atom space?
No, every block is in the 3D space map.
Okay.
So again, I think it's only the gold blocks and the game characters which are actually pushed to the atom space right now, as well as their immediate relationships, like such and such is on something, such is near something. That's kind of a bit of a compromise for now because of constraints on the atom space side and access and everything else. But one day, who knows, maybe we'll have it all. Any other questions about that?
What is the technical limitation that currently prevents loading a bigger game world?
Right now, it seems to be just that it takes too long to in the perception action interface to actually communicate stuff. I think it's strictly a problem with the PAI though. I think if we could get all of that into the 3D space map in the atom space, I think it would be fine. So we're looking into that. We don't have anybody that's just working on PAI right now, so we haven't had time to dig into that really.
Now, if you wanted to put the system in space to control a spacecraft near a black hole where space and time are distorted, you need a 4D space-time map.
That would probably be more useful than a 3D space map. Okay. So for the questions I put to you guys before, does anybody want to know any more detail about the non-AI parts of the Unity game world, since we've already gone over most of the connection with OpenCog?
One interesting topic is, which I would like to know more about,
Sure.
is like what would need to be done in Unity to go beyond individual canned animations for actions. So if you're controlling a robot, you're controlling servo motors or Tilden style integrated fire digital or analog neurons or something, right? So
Yeah.
in theory, in Unity, you should be able to do that too, but what will be required in Unity to control the agents with virtual servo motor commands for their joints rather than canned animations?
Yeah, so Nikki was looking into this for us. So the Unity recently came out with this Mecanum animation suite, basically, where they use these blend trees, which the blend tree is not a behavior tree, but it does sort of decide moving between states. It's more similar to a finite state machine, really. And for maybe give a different example, what we were looking into was the possibility of trying to set up different canned animations.
So you predefine a skeleton, and then it assigns movements to the different joints of the skeleton, or how does it work?
It's more like you define a rig, and then you define certain canned animations for particular states in the rig, like what they're showing here, and you move between blends of those states. So you basically take each extreme that you might want the character to do on each part of the rig, and then you blend that between the different parts of the animation that you wanted to do. So like if you wanted to blend between the run forward and the turn left to 30%, then it will turn 30% left, right? When we were investigating this, Mickey's new rigs could probably handle this, but we're not sure how we would connect the blend trees and behavior trees together to make the logical sense of when and how we should blend animations. The other problem that we are encountering is that the gameplay design that we have right now isn't perfect for like full 3D movement like this is. And we mostly had to design with the understanding that you would only be able to sort of be in one block at a time. We could change that, but it's going to mean a whole new host of animations and stuff. I mean, the other way to do it, the only other way to do it that I know how is to build a whole inverse kinematics engine and then have the planes from OpenCog be detailed enough to like always be the lowest level of granularity possible. I was giving you an example before.
I think that it wouldn't have to be necessarily the plans from OpenCog. There could be some intermediate layer that translated OpenCog's plans into the lowest level possible. But as we use Destin we use as an intermediate layer to translate images into atoms, right? So there could be an intermediate layer between the higher level movement commands from OpenCog and the lowest level servo motor or virtual servo motor commands. Right? I mean, you could view that as a kind of hierarchy similar to the perception deep learning hierarchy.
Yeah, I mean, I was talking before about trying to build kind of a hierarchy like that, like, I mean, in this case, the drag, foot, stiff, knee, walk, forward move or something, where these translate to a limp later on. But I guess part of it is, when it comes to the actual animating in Unity, right, we have to have something like Lentry Mecanum.
So if you want to do your own inverse kinematics, how does that work in Unity then?
I think that we would have to use Pro version. and dig into their animation classes and do it ourselves, basically. I don't think that there's a free version or a non-pro version of inverse kinematics implemented in Unity.
And if you use the pro version, of course, that would still work in the player for free.
Yeah, that's right.
Because it's just like anyone could download and play a game. But it would mean anyone who wanted to develop would have to buy the pro version.
Yeah, if we couldn't find some way to package it, like maybe we developed it in the pro version, but we sort of sent out like a release as a DLL that somebody can just import in on the free version or something. But it might be a fair amount of work. Also, I mean, it's notable that all the implementations of inverse kinematics in Unity are free right now. So I mean, they were large development projects, large teams.
How much does the pro version cost?
Of Unity?
Yeah.
Let's see. So yeah, 1,500.
Hong Kong Poly you could afford that.
Probably good. We already have one pro license.
Oh.
But yeah. So yeah. So that's kind of how we've set it up for now.
Are we gonna port to the BlackBerry 10?
Why not, right?
I don't like Linux.
But yeah. So I forget now what the three choices I put to you guys before, but it was going deeper into the Unity side, how we do particular like action implementations and stuff, or trying to build the player of this version and put that on the USBs and get that up together. Option A. Okay. Well,
Could I ask a separate question?
Sure.
Starting here too?
sure.
I just have a brief text document that shows the atoms related to the home object
Sure.
and the links or the links to the nodes related. I wondered if you could kind of show that and explain more or less what each one is for.
Well, I don't have a visualizer for the atom space, if that's what you're asking.
No, he's not.
No, I mean, I have a list in a text document that has like 10 atoms.
He just wants to ask you for each of 10 atom types what they are and why.
Okay. Well, I don't know that much about the atom space, but
But between the two of us, we may be able to answer the question.
yeah.
If you have Skype, I can just
Sure.
make it appear on. Thanks.
The Hansen face.
Okay. So pet home, like you said, is basically the hearth block, or the location around the hearth block where it will feel safe. This is the ID of the object in the Unity game world. That's to help us track and to keep track of how it exists. This is, yeah, some of the reference. I guess this is where it actually connects the ID of the object to the perf itself with an inheritance link. I'm not sure what these represent, although this seems to me as though it, these AV values, something like the OpenCog, like goal or motivation values or something. I have a feeling that the number node here corresponds to it actually feeling safer, and it recognizing that it feels safer.
Those aren't attention values?
Is that what that is?
I assume.
Okay.
I mean, you have TV truth value, AV attention value.
Okay.
It would seem.
Oh yeah, you're right, because then it's short term. Okay.
I'm not sure why they're all negative 1,700.
Yeah, I'm not sure why they're negative either.
They're very, very unimportant. Or the minimum, yeah, that's that. Where, how exactly was this generated?
By taking the object node ID and looking at the incoming set.
It appears to me that those are attention values, and whatever was supposed to be done to initialize and propagate those may not have been done, so they're just full of gibberish.
It's possible. I mean,
Because they haven't been working with the attention allocation in the game world yet, whereas in the previous game world, when Genois was doing the experiments with the little robot and the batteries in the house and so forth for his thesis, he was running attention allocation and had a forgetting mechanism for forgetting of unimportant items and so forth. So he was doing some dynamics that are probably not being launched in the current version, which made those attention values not be meaningless.
And what is the scene node? What does that mean?
A scene is a word sense, basically. That Linus liked that word for some reason. I don't know. Yeah, it's not a semen node.
unfortunately. I do know this is the ID of the NPC character. When you do the load command from the command line, any name you give it will be the name that it will be referred to in OpenCog this way. So if you do load NPC, it will be like
So
OAC NPC.
it's still a pet node, huh?
It is for now. I know these things are a bit archaic and old, but we're working on it. Okay. Well, what I can do is try and get some code that I think Alex is working on right now, and try to show you guys an example a bit later. If there's no more questions, or if people would really like to get a player today, then I can work on that. Does that sound good? Okay. Well then, what would you guys like to do?
Upload into a superhuman robot and fly around in space.
I knew I shouldn't have asked you that. Bridging, were you going to go over the...
She's going to do that probably after lunch.
Okay.
But I have a little more material. So go ahead. She's currently figuring out what she's going to say.
Okay.
I don't know, maybe she figured it out already. Actually, Ray, are you ready? Doesn't look like. She has to finish a game of Pac-Man. I'm going to now take a bit of a step back and talk about AGI from a more general perspective, and less about the details of OpenCog. And after that, we can dig back into the details of OpenCog more. So first, I had a couple general comments about the game world stuff that Lake was presenting, and some of it also applies to the robotics work that we briefly alluded to. I mean, one of the comments that Matthew made to me, so Matthew Shabir, who's sitting in the back, is not an AI researcher, he's actually a sales and then business operations marketing type guy who has been working with me with an aim toward bringing more money into AGI and into OpenCog, which is a medium-term pursuit, but an important one. And I invited him to come just to get a broader feel of what the whole AGI field is about. And one of the comments he made is it struck him how each little piece of OpenCog required so much work, and that was a long story unto itself, and has so many little tiny research problems inside it, and each detail you look at, you open it up, has more and more details to it. And I mean, to those of us who have been working in the field for a while, this is certainly no surprise. But I mean, it's a large problem, right? And if you look at something like IBM Watson, I mean, that took IBM, 25 PhDs, a bunch of support staff running their supercomputer, and that was like 4 years of work for that team. And what is it? It's a giant expert system, right? Almost any one of us in this room could have architected that system with 6 months of effort or something. Building it is a whole other thing, because it's large. There's a lot of rules. There's a lot of text bases they use to mine knowledge from and so forth. But in concept, it's nothing different really than what was being done in the 70s and 80s with expert systems. It's just very scalable. And yet, that's 25 highly paid IBM employees over a significant period of time. So if you ask yourself, and this is not necessarily an inspiring point of view, but if you ask yourself, like, how much bigger is OpenCog than IBM Watson? Say in maybe 10 times? So then if you chose to scale up the amount of effort spent, you say, well, that would take 250 highly paid IBM professionals for years. But of course, there's the mythical man-month phenomenon, right? So you can't really scale a team by size 10 and have it take the same period of time. So then maybe you're scaling it by 5 and have 125 professionals over 8 years or something, right? And that will be the most direct sort of extrapolation you can do for how big this sort of thing is. So one conclusion to draw from this train of thought is, if progress seems slow on NARS or ERA or OpenCog or any of these systems, it doesn't necessarily mean that you're doing something wrong. I mean, people from outside the field will look and say, oh, you've been working on this for like 5 years or 10 years and you haven't gotten there yet. Or the AI field has been around 60 years, and what progress has the field made? But actually, it's a large task. So, I mean, the AI field has gone a long way in 60 years compared to the AI we had in 1920 or 1950. The AI we have now is awesome. And what AI systems can do now compared to 20 years ago is quite amazing in sort of commonsensical terms, even though it's not a human level AI that we're looking at here. I don't necessarily think that estimate of, say, 125 people for 8 years is necessarily what it has to take. I think that, history shows that you know, large companies are not always the most efficient at getting more done for less, and a small group of highly dedicated people working hard with the right idea can sometimes get done what a huge team in a big company or government agency could not do. I mean, there's loads of instances of that in the technology industry. I mean, I'm sure IBM's PC team was probably much bigger than that. The amount of money they spent making the first PC was probably quite large over a long period of time with dozens of highly paid engineers. And then, you know, Steve Jobs and Steve Wozniak in their garage pieced together the Apple and grew that on a shoestring without that much time as IBM spent brewing the PC, without nearly as much money either. So that's sort of comparable. It doesn't mean that things have to take as long or cost as much as you would extrapolate from that sort of reasoning, but that's sort of a baseline to think about. And then if you're not going to do it that way, that just means you have to have a really good idea and be really smart and agile at doing what you want to do. So part of one thing in the line with this general observation that each little part has so many details and is so much harder than you would think at first is that this game world business. I mean, at first, for me, not being a video game guy, I mean, I very rarely play games since going to college at age 15. Before that, maybe middle school, first couple years of high school, I probably played more Pac-Man than I should have. Early 80s games, but since that point, playing games has never seemed like something I felt like spending time on. But yet, I could really see the value of a game world for AIs, and I sort of naively thought at first, well, you know, this is not research. This is just making little guys run around on the screen. This must be really easy. It must be like a couple months of work to get a game world together for the AI to play. And of course, when we first started trying to build the OpenCog game world, we had AI developers doing it sort of in their spare time, and that they made some questionable choices in the architecture within the game world. And then we brought in Lake, who's a professional game developer, who had to unhack a whole bunch of things and has been doing the development basically right, but it does take a while. And this is after some earlier efforts, which were just in multiverse and Second Life and so forth, which were pretty much total hack jobs done by AI developers in their spare time. So one thought that I had a while ago, which our current game world doesn't yet live up to, but may, is it'll be nice if every AGI project didn't have to go through the same process of like hiring a game developer and learning how to use Unity or some game engine and doing all this work to make a world where your AI can control characters. And what I'd like to have is a game world, perhaps this one with some API improvements, that anyone who had developed an AI could just plug their AI into and use the API to control an agent and get perceptions back. And then you have a sort of universal testing ground for anyone's AI system or anyone who's interested in virtual embodiment of the AI system. And you could use this for sort of systematic comparative benchmark testing of AI systems, where you make some like virtual world IQ tests in the game world. To me, that's not as interesting as just qualitative comparison of what different AI agents can do. And if we had a NARS-controlled agent, an OpenCog-controlled agent, an ERA-controlled agent, various other ones like playing and interacting in the same world, it would just be quite interesting to see what they do, how they interact with each other, how they trick each other. I mean, just to pick on Pei again, just for fun. Since since the NARS agent doesn't use probability theory, if the OpenCog agent, say, started playing a gambling game with the NARS agent, could it win all the money from the NARS agent? Because the NARS agent was using non-probabilistic logic to calculate the odds. Because that's one of the foundations of probability theory, is that if you measuring uncertainty using a non-probabilistic method, you can kind of use like Dutch book gambling methods to win money off the non-probabilistic agent. So probability theory is sort of the only way to measure uncertainty that won't lose you money on gambling in the long run. But that's probably not the most interesting thing you can do. It would, I think, to see a bunch of AI agents controlled by different architectures trying to cooperate together as a team to achieve some goal in the game world would be quite fascinating. Probably more so than having them all take some IQ test in the world. Because the issue with positing a test is all these architectures are so flexible. People can always tinker with their architecture to make it do well on that test, which is always the most interesting thing. And I think we're not that far from the world that Lake is building with support from Nikki and others in Hong Kong. We're not so far from that world being usable for multiple AGI or proto-AGI architectures to interact with. And one thing that could be done, which would be interesting, is like make an online version of the game world. So you just have a website, you have a game world that can be viewed online through a browser, and you have some characters living in that game world. And then basically anyone who is a member of the site, a professional member or whatever, can use their AI system to connect by some socket to one of the characters. So you'd have like an online AI aquarium or whatever that you can look at on the browser, and everyone can log in and watch the different AIs and interact with each other. And there's nothing extremely difficult about that, given the foundation we have now. I mean, someone would have to take time to do it, and then we'd have to get some other AI project to want to do a little work to connect their AI to the game world. Now, ultimately, I think OpenCog is going to work, but I mean, as you've seen from my review of the OpenCog architecture, I'm pretty open to stealing other people's ideas. Well, borrowing other people's ideas, I mean, with credit. I mean, I think different AGI theorists tend to have focused on different parts of the problem, so that different architectures often have a lot of algorithms, structures, and so forth to contribute in specific areas. And ultimately, the existence of like branded AGI architectures, like this is the OpenCog architecture, this is ERA, this is SOAR, this is LIDA. The existence of these branded architectures is largely based on the need of academics to publish things. So you need to give a name to something and publish it and write papers about it. But in fact, the branded architecture is not always the most important thing. Because each of these architectures, in the end, combines algorithms and structures that came from a variety of different sources. I mean, NARS is relatively pure. If you take something like LIDA, I mean, he has Hofstadter's SlipNet, he is, I'm forgetting the Finnish guy, but he has some, Kanerva. He has Kanerva's sparse distributed memory in there. I mean, there's a lot of things from different sources. So by having a playground where people could see each other's architectures working on the same problems that their architectures were, that would certainly foster understanding of what each other were doing, and probably more flow through of ideas from one project to another. Because right now, it's actually very hard to compare different AGI approaches, even qualitatively. I mean, I don't really care about a bake-off if we did 0.9 versus 0.901 on some test problem, but just to qualitatively understand how different are the architectures and how they're approaching problems it's not particularly easy because we use different representations which may not really be as different in behavior as they seem to be the way they're written down, and then we tend to focus on different kinds of problems. So this same, and actually, I talked to some folks who wanted to make a commercial video game based on this idea, which didn't end up coming about, but it was an amusing idea. It was supposed to be an MMOG where there would be different gods, and each of the gods would be controlled by different AGI architectures. You have the OpenCog god, and the SOAR god, and the NARS god, and then each player would have to worship one of the gods. And the mode of worshiping the god, unfortunately these are retarded gods. So the way of worshiping the god is to teach your AI god to make it smarter and smarter. So if you have taught your AI god to make it smarter than the other AI gods, then ultimately it will win the game. Yeah, I have no idea if that's a good game idea, but it's funny. And maybe something in that vicinity will happen eventually. But the beauty of that sort of idea is that it's a game design where having many different AGI systems participate and interact with each other is just part of the game. And I mean, if we're really successful, we will build some new gods too. So it's always a good thing, I guess. Now, most of what I just said about game worlds holds equally or more so for robots, because dealing with robots is a big pain. And I mean, the robots, they break, you have to replace the motors, you have to deal with all sorts of low-level perceptual issues. Like, okay, you have a robot with a nice hand, can it really pick up this eraser or not, or do you have to do a lot of scripting in the action control language of the robot to tweak the way the fingers work to pick this up? In terms of vision processing, no robot now comes with a computer vision library that is like ready to be plugged into an AGI architecture. I mean, you can use OpenCV and other computer vision libraries to build a vision system for a robot, but there's not a collection of modules you can plug in that would just, okay, now I've plugged this in, now my robot, it will navigate and it will send the SLAM, the map information back to the AGI system, and it will tell me there's some object at this coordinate or this coordinate with these properties. I mean, there's nothing like that, which just lets someone who's not a roboticist plug their AGI or proto-AGI architecture into a robot without having to spend at least many months of their time digging around with the robot, and maybe more than several mad months of time. We're moving in that direction with things like ROS, the robot operating system, developed by Willow Garage, and the Aldebaran now has a nice API, but we're still not yet to the point where we have a kind of plug-and-play software package for a robot, which gives an abstracted perception and action API of the sort that someone developing, say, NARS, to take one example, could use to control a robot. Say something like NARS is not at the moment well equipped to deal with low-level perceptual and action data. So what you would want to hook it up to is, say, some vision API that just gave you basic information about what objects are where in the room, what they may be, what places are reachable if you walk. And then for action, you just want step forward, turn right. If there's some object, does it look pick upable or not? And then if it is, you can send an action to pick it up. And with this sort of API, you wouldn't be able to do everything because ultimately, I mean, eye-hand coordination is important. And if you want to train your robot to be a concert pianist or a good athlete or do something complicated, it's going to need to interface cognition, perception, and action in a subtle way that goes beyond what you could do with a canned API that encapsulates perception and action from cognition. On the other hand, you can learn a lot just by connecting various proto-AGI systems to a robot using a clean and simple API that let them, within days rather than months of work, control a little robot walking around the room and perceiving and acting. And I think that's a bit harder than what we're doing in the video game world, but it's along the same lines. And ideally, you want to have almost the same API, so that once you control the game character from your AGI, then with minor tweaks, you can control a robot. I mean, you may not be able to get it 100% the same. I mean, for example, the map of the world from a video game, you can get it to be exact, whereas the SLAM, simultaneous localization and mapping maps you get from a robot's camera eyes are fuzzy and or probabilistic in nature. You're not going to work around that, and you can get more accurate information about whether an action succeeded or failed from the game world. Whereas in the robot case, I mean, that relies on the accuracy of your information from the force against the motors and the various sensors in the robot. But by and large, it can be about the same API. And I think if we had a clean system for AGI researchers to control game characters and robots using the same API, working with a variety of commercially available robots, ideally with some open source robot as well as some good commercial ones, and with a game world like the Unity world that Lake is building, and potentially other game worlds could be built utilizing the same API. I mean, it's a lot of work to create a game world like this. On the other hand, once you have an example, it's always easier to copy that example than build something totally new as well. I think that this would have a quite good impact on the AGI field as a whole, and it would allow different researchers to really compare their work with that of others at a level that doesn't happen now. And it would also push things a bit in the embodied learning direction, which, according to my philosophy, is probably a good thing. Because right now, I think there are more researchers who think embodiment is a good idea than there are researchers who want to mess around with it in practice, because it's a pain. I mean, making a system that interacts with text files in some way or another or on the command line, it's a lot more in reach as, say, a single graduate student working on your PhD than controlling robots or game characters. And that's totally understandable. I mean, I think if I were doing a one-man AGI project, it would probably be a mathematical theorem project, because I like math, and that's easy for one guy to program. Whereas all this stuff with robots and embodied characters, if you're one guy, you wind up spending all your time having to deal with the world stuff, rather than with the mind stuff. So I think if this sort of platform were available, a lot of people who are not now working on embodiment-related stuff would have an interest to try it out. I also think from the standpoint of getting government funding into AGI, this sort of thing can be helpful, because what government funding agencies want is something with very well-defined metrics and milestones for measuring and comparing things. Because the government program manager needs to be able to justify to his boss that he didn't waste more of the government's money than everyone else. Right? So if you can say, well, we demonstrated that all the participants in this AGI funding program improved on this metric by the required ratio of 5 times since the beginning of the project, then the program manager's ass is covered and everyone is happy. And that's actually a tricky thing to do with AGI, to find a good test of incremental progress for AGI. You know, constantly people approach me and say, why don't we do an X Prize for AGI? Like Peter Diamandis and the X Prize Foundation have made these prizes for doing various cool technology achievements. I mean, the Google X Prize is like send a rocket to the moon and have it send back some video, right? Then there's the Tricorder X Prize is to make some handheld medical imaging device so you can scan around a person's body to find all the problems with their body. And these sorts of things make sense. Now, why can't you do an AGI X Prize? And I thought about it a lot. I couldn't think of any way to do it that wouldn't just be susceptible to hacking and gaming and become a narrow AI X Prize of some sort. I mean, let's say you tried to make the equivalent of Wozniak's coffee test, but with something somehow more sellable, like go into a random house and make coffee. I mean, it could be search and rescue, for example. Like go into the rubble of a burning building and then bring out the flaming kit or whatever it is. So, I mean, if you do that as the goal for a contest, pretty much in each case you find like either it becomes too hard, in the sense you really need a human level AI to do it. And if it is that hard, the problem is no corporate backer wants to bother to fund a research team to chase something that looks like it's going to be 5 or 10 years away. Or it's easy enough that what you can do is just engineer a specialized robot to go into burning buildings and rescue kittens. And this problem, I think, gets at a basic difficulty of AGI, which is that for any highly specialized ability, it seems with various tricks, you can figure out how to get, I don't know, 70–80% of the way there using narrow AI and various tricks. And especially if your goal is to fill a certain human function in the everyday context rather than a specific technical specification. So, I mean, web search is an example. Natural language search, where you can ask a full question in natural language, that hasn't advanced very well at all. But the world has worked around it by making keyword search that's better and better and better. And we've all gotten kind of used to typing in. You know, our minds have adapted, so we're good at finding like what are the 5 keywords I should put in to get the answer I have, the answer I need. And we've kind of worked around the need to have good natural language. So, yeah.
Are you aware of anyone that's tried to make like an automated test suite for an AGI? Some sort of project like that?
I am aware of many people who talk about it and think about it.
Yeah.
And whether anyone has tried to make it, I don't know. But I'm not aware that anyone has released such a thing. And I think that the real difficulty is that things are just kind of too easy, or they're all the way there. I mean, a rough conceptual analogy is like escape velocity. You get into outer space, right? I mean, like if either your goal is to get the thing into orbit, or otherwise other technologies that are different than the ones to get things into orbit may apply. Like if your contest is to get something 1,000 feet up in the air, that may be useful for some things, but the technology you need to get something 1,000 feet in the air, cheapest and fastest, may not actually be the same one you want to use to get it into orbit. So, but one thing I thought about a bunch and wrote something about was like taking IQ tests for kids aged like 4 to 7. So they're special like child preschool IQ tests, and you can take these IQ tests and either give them to an AGI or adapt them very manually so that the blocks the kid moves with are not hard for the robot's hands to use or something. You can take these child IQ tests and give them to an AGI system. And the conclusion I came to is that would be really interesting as long as you weren't engineering your system for the test. But if you took the like 10 modules of that child IQ test and just engineered a system to do those 10 things, you could do that. Like there's certain vocabulary problems and problems with rearranging blocks in a certain pattern. I mean, no doubt you could engineer a system for each of those things. I mean, and that's even kind of like saying you could take a kid and if you spend a year drilling them in those exact 10 capabilities, even if they're kind of a dumb kid, you could probably get them to have an above average IQ on that specific test. And I'm sure there are schools in some countries that do exactly that, right? So, but if you didn't teach them the test, then those child IQ tests actually seem interesting as a test of intelligence of young AI systems. So the problem is the ways you can cheat with an AI are so much more than the ways you can cheat with a young human kid, right? Because we can't like open up the kid's head and like rewire the brain to the test. The most we can do is drill them and teach to the test, which is a little harder. And that obstacle has been there for the people trying to make these kinds of test suites. So it's when you really get into it, I'm not saying it's a bad direction. It's one of these things that seems much harder before you start doing it than once you actually do it. Because you're always, on the one hand, stuff that with a bunch of hacking, someone could hack something to pass that exact test, even if not in the spirit of the test. And on the other hand, things that seem like they're AGI hard. Like an example is conversation. Like, okay, to pass the Turing test for an hour, like have a conversation for 1 hour with the AI system in a way that you think the AI is human. That seems like it's AGI hard. Like you really need a human level AGI to do it. Now, to pass a conversation test for 5 minutes, I don't know. The systems have come pretty close now. So by hacking together like statistical linguistics based stuff with a bunch of conversation rules, you might be able to make a system that would fool judges into thinking you're intelligent as a human for 5 minutes in a way that's a total dead end for research because it's just hidden Markov modeling and chat rules. But it seems not to scale continuously. Like when you get to 15 minutes, that's like really a technique halfway between the 5-minute technique and the 1 hour technique is going to work. Because somewhere there's a shift between using highly specialized methods and making something that learns. So it's an interesting but tricky problem area.
There's this Spanish guy who made the website.
This consciousness test, right?
Iconscale.com.
Yeah.
Calculator and everything, we can check your agents.
Yeah, that's true. That's true. I remember that. He gave a talk in Hong Kong at the workshop of machine consciousness, the sort of science of consciousness conference. Yeah, that's interesting. I mean, I guess to be honest, I don't remember the nitty-gritty details of that, but I do remember thinking that it didn't really solve the problem.
No, it's too simplistic, I think.
Yeah, but that was an effort. I mean, if something good like that were come up with, it would certainly be helpful for the field. But I think it would somehow it would have to be a broad array of possible tests or scenarios, and which one was going to be given to the AGI system would have to be chosen at random at the time of test taking. Like if you think about the preschool IQ tests, which are kind of word association, question answering, rearranging blocks in a certain order, and if you had like 10,000 different things like that, and the kid didn't know which one would get thrown at them in the course of the test, then you're getting something that would be more and more and more of a pain to engineer a system for, right? Because if you kind of think about like if you were a psychologist giving a kid an IQ test, but you knew that these kids, they were all coming from different countries where they had been brainwashed just to do well on IQ tests in different ways in each country, but they'd been taught to the test in some way. So then you had to find a way to test their IQ that would get at the crux of the matter and bypass all the teaching to the test that the different governments of the world have done. Then it's sort of that sort of problem, which is a weird one. And I guess ultimately, for my own attention, I decided, well, that's interesting, but that's harder than I thought. I'd rather just focus on building an AI since making a test seems like not a tiny spare time pursuit. But yeah, the U.S. National Institute of Standards should do it. I mean, that's their purpose, is to make standards for measuring everything.
I thought the idea was that other people make the standards and they just simply stamp it.
Yeah, pretty much. Well, they're more diverse. You know, James Aldous, he developed one of the world's best infrastructures for unmanned automated vehicles. It was a 4D RCS architecture, intelligent unmanned automated vehicles. And that was all funded by the National Institute of Standards. I'm not sure why. It seems totally not within their mandate. But I think in the last 5 years they've gotten away from that, and someone decreased their budgets, and now they're actually only doing the thing they're supposed to do. Yeah, they have enough trouble. Like the reference weight kilogram keeps changing in mass, so they have a lot of their own problems.
Well, I'm worried about another part. The human brain, not like computer. You cannot bigly revise your own brain. If somebody's IQ score is very low, it will be improbable for him to get a high score in the next week.
In the next week, yeah.
Yeah. But AIS is different. OpenCog, you competed with NARS for the people say, well, this time I lose, I will revise it. And next week, you will have an updated version. And OpenCog can do the same thing. So
if they updated it to make it genuinely smarter, then at least science is progressing, right? The problem is if they upgrade it by having 10 programmers put in a new module especially for that test, right? So that's like within the last few weeks there's been all these newspaper headlines like, AI is not as smart as a 4-year-old child, and then the skeptic, so AI is not even as smart as a 4-year-old child. I mean, what all this is about is some university researchers used ConceptNet, which is a database of kind of word meanings and word similarities, and a little more abstract than WordNet, but they use this to make a system that can answer some vocabulary and similarity matching questions in a manner like a 4-year-old child. Like what's more like a dog, a cat, a pig, an elephant, or an airplane? So the fact that their system could answer these verbal portions of an IQ test as well as a 4-year-old was turned by the university's PR guys into, our AI is as smart as a 4-year-old. And then they added the caveat, but it didn't answer the why questions as well as the 4-year-old. But,
Gosh.
Of course,
the 4-year-olds aren't the ones that answer the why questions.
Yeah. I mean, even if it had answered the why questions as well, the thing is, answering these test questions is a very minuscule portion of what makes a 4-year-old child interesting. And the thing is, consistent with having a human architecture and not being able to intervene in its brain, these tests are an okay way to assess general intelligence. However, in the broader context of having a system that is not constrained to have the human mind architecture, the test doesn't really mean very much. I mean, it's not a general purpose test. It's a test specialized for humans. And so taking it out of context like that doesn't really mean much of it.
But to be fair, I believe that the competing systems should share the basically big database. If one has more experience, certainly it looks unfair.
But that's unrealizable. I mean, there's no way to. I mean, AI. If you look at an AI system, at an instance of an AI system as like its own mind, right? If I took an OpenCog system and we spent 4 years in our lab in OpenCog teaching it stuff, I mean, then just like a human child, it had its own experience and learned from that experience. Now, what you're going to say we have to start with OpenCog with no knowledge and then spend 4 years teaching it in some laboratory-controlled condition? But I don't think that's how it's really going to happen, because I think an AI will accumulate knowledge over time in real life, right? I mean, you could say the same between people, though, right? I mean, if you compare the IQ of two kids, what you're measuring is their life experience as well as the state of their brain. I mean, that's just how it goes. You're not taking a clone of those two kids and raising them in an identical laboratory condition and seeing whose brain is smarter, right? I mean, you're measuring their brain capability and how well they're taught and what they experience. So I mean, I think that's how it is between people too.
Yeah, just like we can compare the intelligence of twins. They are brought up in the same environment. Maybe there is an OpenCog system brought up within one environment, but another system brought up in another. But the two environments are basically the same. We have some experimental control on the sameness of the two environments. For example, they are reading the same natural language text, but they have different unit programming procedure to deal with those texts. No matter what kind of method they use, what we need to guarantee is the sameness of the inputs on the natural language.
You could do that. I just think that is not going to be how it happens. I mean, of course you could do that, just like you could do that with human beings. But it's not what we do with human beings either, right? I mean, I think that in practice, an AI is probably going to accumulate knowledge over time.
Yeah, that's right.
Through its experience, and then...
This is what I believe, yes. I just say that in AI, because in a video game environment, it's more easier to control the sameness of the environment.
Yeah, it is, but if an AGI is going to achieve an advanced level of intelligence, that will be due to lifelong learning, right? I mean, it's going to be because it learned things day after day, week after week, month after month through its life, and then to rerun that kind of experiment is very slow, and it takes a long time, right? So I think as long as our AGI systems are really stupid, and we're in a very early stage of development, you can do that. Like you can do that right now, but as soon as you make any progress toward a genuine AGI system that can think and learn like a person, then you're already out of the domain where you can do that, because it's going to be more like a person in that its life experience will have shaped its intelligence. And to the extent that it learns from interacting with people, there's a certain limit to the rate of learning, because the interaction with people happen on the human time scale, right?
I think that this is just a problem of time and patience and urgency. We can build up a super environment just like a movie, Truman's World, okay? Everything social interaction. If you have money, you do that.
In theory, but the question is, while you're doing that, some other AGI system has been taught in the real world already and is learning more and more and is smarter than any of those systems that had to start from nothing in the true world, right?
So, well, I mean, the proposal just to comparing two agent system in order to be fair, just one.
No, I agree that that would be the right way to do it, to compare systems to be fair. I guess my feeling is that in real life, what will happen is once some AGI system has been gotten to the point of doing actually obviously intelligent things,
Yeah, that's right.
then people will just run with that and make it smarter and smarter. And
Yeah,
comparing to be fair with other things
yeah.
is irrelevant, right? I mean, that's how technology seems to work in most domains. You have competing things. One of them catches on for whatever reason, and then it just grows. And it might be that something else actually was better. I mean, just like all the examples you see in business school, like VHS versus beta video cassettes or something. I mean, the Mac versus PC or whatever. I mean, these things really never go by, let's do a completely fair comparison.
Yeah, that's right.
Uh,
Oh, I have a running question.
Sure.
Just think about the gambling game, OpenCog trying to fool the NARS.
Yeah.
I believe that NARS at first it will lose money because it uses another thing for the probability theory, and human beings who do not use probability theory will lose money.
Yeah, that's how Macau works.
Well, that is
Right.
philosophical problem. That's not philosophy. Another technical problem. The philosophical problem is most uneducated human beings will be the victim of the Deutsche book or the computer policy.
Yeah.
But intuitively speaking, we are smarter than computers. But so is the competence in gaining learning in a special case the mark of intelligence?
Well, here's an interesting point. If you take a bird, say a crow, or a parrot, or a sparrow, right?
Yeah.
Take a bird and give it some food here, some food here, and some food here, right? And then make it uncertain. So each day there may be some food here or not. There may be some food here or not. There may be some food there or not, right? And then you measure how often does the bird go here to get food? How often does the bird go here to get food? How often does the bird go here to get food, right? And you can vary the amount of food that goes according to different probability distributions. What you find is a bird will forage for food correctly according to the solution of a multi-armed bandit problem from probability theory. So birds follow probability theory in searching for food, and so do many other animals. So this is unconscious, right? Not by, the bird is not saying, well, the probability of this plus the probability of that divided by this is so and such, right? The bird's unconscious brain is using probability theory to choose where to forage for food, and I bet that primitive humans do that too. Like I bet if you put a college student in a bar with a bunch of girls that he's interested in, he'll probably use the optimal probability theory to go among the girls in the bar, right? So I think we have some unconscious capability to do probability calculations. And then as you say, we also have, some of us also have a conscious, rational ability to do probability calculations in our minds. But there's plenty of people who are good at gambling by gut feel, without knowing anything about probability theory or anything about calculation as well. So I think it's complicated, right? It's not fair to say that probability is just a formal theory that people learn the way that they would learn, say, the theory of Hilbert spaces or abelian groups or something, because it is also wired in to our lower level brains in a way that's shared among us and other animals. So what Pei has to argue is that probability theory, yes, is wired into our brains for animal level activities, and is something that we can learn at the highest level abstractly if we're mathematically inclined, but in between those two layers there's this different logic. which is not impossible, right?
But why do we commit conjunction fallacy? It is against policy. 90%
Because our brains approximate probability theory very badly using Hebbian learning. We're just not that smart. So, if you're trying to estimate, let's say you have one. So, to explain any one of these fallacies is tricky, but if you, in general, think there's a bunch of cortical columns in the brain with a bunch of neurons in each one, and say some, in the simplest case, a collection of columns, more generally a pattern of activation among many different columns, represents one concept, and then some other collection of columns, a pattern of activation among columns, represents some other concept, and so you have a bundle of synapses between the one or the other. Then Hebbian learning has learned that when the cell assembly A is active, then afterwards the cell assembly B is often active, right? And then the weights of these synapses are increased, and that will tell you something about the probability of B given A. It's given roughly by the probability that when the neurons in this cell assembly are active, then the neurons in that cell assembly are active, right? So this sort of conditional probability of activity of cell assemblies has to do with the weights, right? The long-term potentiation of the conductances of the synapses between this cell assembly and that one. And you can roughly see how probability theory comes out of cell assemblies there. Neuroscientists do this. There's a huge literature on information theory and Bayesian population modeling among populations of neurons. So this stuff is measured in various cases of motor learning in animals and so on. And, it's just a mess. The brain is estimating conditional probabilities using probabilistic population coding in populations of neurons, but there's all this weird nonlinear dynamics on different time scales going on. It's not that exact, and there are quite systematic errors. So actually, there was a project called Icarus, which was funded by the U.S. government, and which I was involved in for a couple of years. And the whole point of the Icarus project was to simulate 7 regions of the human brain and their interaction using a detailed computational neuroscience model. So we're using integrated fire neurons, then Izhikevich neurons, and more detailed neural models to simulate why humans, when analyzing data, have cognitive biases, why they make the conjunction fallacy, the probability fallacy, all these standard cognitive errors. So to simulate why humans make cognitive errors based on a detailed neural net model of parietal cortex, medial temporal lobe, and various other parts of the brain. And there was 3 different teams involved in this. The thing ran for a few years. And you come up with reasonable explanations. It's not very hard to make a neural net model of these parts of the brain that will appear to demonstrate these fallacies that people give rise to when reasoning.
Yeah, maybe I can figure out where the fallacy comes from this model, because this P&A means the probability of people who cell firing under the condition of able to fire But what the point in the product problem, for example, in the probability calculus, what kind of probability of B concept object's occurrence and A object? There are 2 kinds. One is internal physical construction, other external things.
For example, So I guess the thing is, in the Icarus project, we found, both in the team I was working on and in the other teams, it was really not very hard to simulate a long laundry list of human cognitive biases using a neural net model of how different parts of the brain work. Most of these neural net models are based on probabilistic population coding, where a population of neurons is representing probabilities in terms of how often they fire. Now, in a totally different direction, if you look at the papers of a guy named Dirk Aerts, he thinks that the brain follows quantum logic, and so he has gone through all these different fallacies of reasoning that the human mind has, and he has shown that his quantum logic model of the mind explains why the human brain gives the conjunction fallacy and the probability fallacy and all this. So I mean, the fact that NARS can sort of explain these errors of human reasoning doesn't really matter. I mean, you can explain those errors by assuming the brain follows quantum logic, or you can explain those errors using detailed computational neuroscience models. There's a lot of ways to get a system to be stupid, basically.
Great question. Do you believe that the quantum model of mind used for real?
That's a subtle question, actually. I mean,
It's very complicated.
I think that if you look at Dirk Aerts and Harold Ottensbacher and some other theorists, what they argue is that quantum logic may sometimes be the best way to describe a classical system, depending on the observer's relationship to the system. So, in essence, quantum logic is the logic of that which cannot be observed. So if a given observer, by virtue of his relationship to the system, cannot observe certain properties of that system, he should reason about that system using quantum logic. And so if you follow that point of view through AI, it becomes quite interesting. And then you come up to the conclusion that the mind should be using the quantum reasoning in some cases and the classical reasoning in other cases. And I haven't fully thought through all the implications of that, if it's true. But one interesting thing there is that the use of quantum logic rules for reasoning is separated from the question of whether macroscopic quantum phenomena are important for brain dynamics. And it could be either one or the other, or both in unrelated ways, right? So you could have macroscopic quantum dynamics in the brain in a way that doesn't help the brain be particularly smart or do any kind of clever quantum computing. And the example is that many birds use quantum non-locality, macroscopic quantum voodoo, to figure out the direction of the Earth's magnetic field, which is very nice, but I mean, an airplane uses magnetometers to do it better without any weird quantum effects. So, I mean, just because quantum mechanics was used for something in the brain wouldn't necessarily imply the brain is doing some kind of super smart quantum computing. I mean, apart from the fact that we don't have any evidence that macroscopic quantum dynamics are used in the brain. Somehow you need to get 4,000 protein molecules to be in an uncollapsed quantum state. And it's not clear how that would happen, but it's not impossible. I don't know. So that's I could give a summer school on that, but that's not the topic here. But it is interesting.
Another tech problem, just back to the gambling case.
Yeah.
NARS ruled the first time. The NARS is systems which can learn from the failure of the past and figure out why I failed. And he will ask for help from other sources. So in pay system, probability theory can be used as a toolbox.
Well, in theory, a NARS system can either invoke probability theory as a sort of code library, or in principle, a sufficiently smart NARS system could learn probability theory.
Yeah.
And then it would invoke probability theory just as some formal system that it had learned. I mean, just like if I gave you some arbitrary set of axioms, eventually, you're a smart guy, you can learn that arbitrary set of axioms, right? So that is, in theory, that is possible. Now, what argues against that most strongly in my mind is the fact that animals already use probability theory to do inferences, and that modeling neural populations in the brain in terms of probabilistic population coding is a good way to explain how, say, monkeys direct their attention between dots appearing on the screen and the different computational neuroscience methods that are used right now. So you just have the science of animal behavior and like current practice in computational neuroscience, which highlights probability theory as there. And I think probabilistic population coding is one of the better ideas in computational neuroscience. It lets you build a bridge from neurons to, you know, Bayes nets and mathematical abstraction. So of course it could be that's all in the wrong direction, but that's still, you kind of have probability theory rising from below in the analysis of neurons and animal behavior there.
When you mentioned ROS earlier, what are the main things that need to be added to make it more useful?
A robot operating system? Well, ROS is just low level. I mean, I think it is useful. It's just, it is what it says it is. It's like the analog of an operating system for robots. So I mean, I think ROS is great, and what it does is lets you kind of slot in one robot in place of another. So if, let's say you have the Now robot, which is that little white humanoid robot that you saw in the video, versus the Hanson Robokind robot, which is about the same size, and it has about the same limbs, looks about the same. I know right now, if you wrote a program using the Now as an intrinsic API to say walk, squat down, stand up again, right? Or if you wrote that same program for Darwin OP or Robokind to walk a few steps, squat down, and get up again. You know, you would have to make different API calls, which is annoying, because essentially they have, it's roughly the same movements for the same kinds of motors. In some cases, like the same dynamixel motor, actually the same physical kind of motor, but it's a different API call, right? So the basic idea of ROS is make an abstraction layer. So I mean, if you have different robots that all have knees and feet and eyes, right, then you can just give abstracted commands to control action plan. We'll make a Darwin OP, a Now, or a Hanson Robokind carry out that series of actions. And that obviously is a very useful thing. And then how far you have abstracted, I mean, you could have a go forward command that would either work for a wheeled robot or for a walking robot, right? So ROS doesn't take it quite that far. But I think what we're looking at as a robot API is a little more high level than that. So, and I think ROS doesn't go there, and I'm not sure it needs to go there for what it is, right? I mean, ROS is fairly universal, and as soon as you start abstracting more, you make more assumptions. But so, say recognizing an object, for example, ROS doesn't do that for you. Like, give me a slam map of the environment, tell me where the objects are, right? Or here is an object, pick up the object.
But it has plugins for stuff like Slam.
Yeah, it does. It does. Yeah, I mean, I think the kind of API that would be useful for people who are AI researchers rather than robotics researchers could be built on top of ROS, and probably should be built on top of ROS. I mean, what you want is like where the objects pick up the object, right? But pick up the object is a higher level sort of command, which involves a coordination of a bunch of different things. And if you're a robotics researcher, you don't want that problem solved for you. That is exactly your domain of research is to figure out how to do that. But what Ross would accomplish is if you had two different robots, each of which had 3 fingers on the hand and 2 joints in the arm, the same degrees of freedom, then at least the same pickup, the object code is going to work for all of them. And the Hanson robots do not yet support ROS, but David would like them to, so I guess they will eventually. All right, so now, well, I've kind of gotten my voice back today. I just noticed that. Yeah. Happened while sleeping last night. I guess having a day of not giving speeches yesterday was kind of useful.
Don't jinx it.
Yeah, it's probably jinxed now that I mentioned it, right? Yeah. So, I'm going to abstract things in a different way for the next bit of the course here, and kind of take a step back in the philosophical direction almost to the question of what minds are and what assumptions about what the mind is underlies the AGI work we're doing in OpenCog and in other projects. I mean, I've given a very engineering-oriented approach to OpenCog so far, which I think that there's a good argument for taking that approach, because even if your way of thinking about the mind is utterly different than mine, you might still find OpenCog a good system to work on. Sometimes it's not always critical what cognitive pathway you arrived at something from. The system and design has value in itself. But the way I arrived at building a system like OpenCog was really quite indirect. Is that I started out with more philosophical thinking about how the mind works, and the beginning of my thinking was not that different than what these deep learning guys are talking about. I mean, you come to the conclusion that for practical purposes, you can think of the mind as a pattern recognition system, which is oriented toward recognizing patterns in the world and recognizing patterns in itself. It can then take external actions and internal actions, and if it has certain motivations, say because it's an animal and wants to stay alive or reproduce or whatever, among the important patterns it's trying to recognize are patterns involving what actions will help it to achieve what goals. And based on the patterns it recognizes there, it can tweak its internals accordingly. And when you view it on that level, it all seems kind of simple. Like all you got to do is implement a pattern recognition module, implement an action module, implement some goals, give it the ability to act, and plug in some cameras and perceptors, and set it running. You recognize patterns in the world. Let it do some random actions. Set it running. You recognize patterns in what actions have helped it achieve its goals, and patterns in what internal structures have underlaid these successful actions. Let it modify itself so the successful internal structures will be used more often. And there you go. And this, I mean, at the time I was originally thinking about this stuff, it was much less in the air than now, because no one was trying to build AGI systems really in the mid-1980s, or almost nobody was. And I came at this more from the philosophy angle, from looking at Charles Peirce and Friedrich Nietzsche and a whole bunch of philosophers of mind and intelligence. And then when you get down to trying to implement something like this in code, you realize that the small module of let's make a pattern recognition module here, is kind of the whole thing. This is actually extremely difficult, because to make a general module for recognizing patterns is just not possible without close to an infinitely powerful computer. So you eventually realize the philosophical observation that, yes, an intelligent mind is a system for recognizing patterns in itself and the world. While interesting, and you can argue it for a long time on a philosophical basis, is not actually very useful, because it just reduces intelligence to general purpose pattern recognition, which, however, can only be solved in general with an infinitely powerful computer. But it does tell you what the problem is. It tells you that the problem is, okay, given the specific goals the system has and the specific class of environments that the system is operating in, how do you recognize the patterns that the system needs to recognize in order to do those sorts of things in those sorts of environments? And this is where things like deep learning come up, because then you say, well, okay, the environments that we tend to operate in are hierarchical in nature. We have patterns and patterns among those patterns, patterns among those patterns, kind of a hierarchical buildup. And so then a network of hierarchical pattern recognition agents seems to make sense. I mean, where I think the deep learning guys perform a kind of sleight of hand is they go from the general philosophy of patterns, patterns within patterns, patterns within patterns, within patterns, and so forth, which kind of is how it has to be. They slip from that to, okay, we have a hierarchical pattern recognition network with a spatio-temporal hierarchy on each level, and these simple neural net or clustering things on each level. And so that's what we need. But actually, that's a very simplistic shadow of the general idea of hierarchical compositions of patterns. And when you try to make a more general pattern recognition hierarchy, you go way beyond the sorts of things that are now being pursued in the deep learning area. So when you start to think about it more deeply, and you see that, okay, so the real problem is how do you do pattern recognition of the important kinds of patterns, the relevant class of goals and environments, then you start to see why the brain becomes such a mess, because what characterizes the relevant class of goals and environments? Well, there's an awful lot of different things, an awful lot of different aspects, and then the brain contains specializations to all these different aspects of the goals we try to achieve and the environments we exist in. But then these different aspects of our goals and environments are not necessarily disjoint from each other. So I mean, we need to do things involving manipulating the body in some detail in order to achieve goals. The goals of like getting food and sex and surviving. We also need to do social interaction, which is a completely different kind of understanding and modeling and learning. But the part of the brain that does the social interaction and is specialized to recognize patterns involving social interaction, and the part of the brain that's specialized to recognize patterns involving dexterity and physical movement, these parts have to work together. And it's best if they can cooperate together, because there are things that involve both social interaction and dexterity, like hunting together on a team, as our ancestors had to do frequently. But also, there should be flow-through. You'll be better off if some of the things you learn in motor learning can help you with social learning. Some of the things you gain in social learning can help you with motor learning. So then, eventually you get to the idea, okay, there's various specialized kinds of pattern recognition we need to do given the goals and environments that we evolved for. And these specialized kinds of pattern recognition, while they each have their own particular characteristics, they also need to cooperate together in some way. And if you follow that line of thinking, then you wind up with a sort of conceptual justification for big, messy, heterogeneous, integrated architectures like the human brain or like OpenCog. I mean, at the philosophy level, it's all kind of simple. You're starting to recognize patterns in the world and yourself that will help you achieve your goals. But given that there's no way to achieve that in general, given the resources available, you want to specialize in different aspects of the task. But you don't want to over-specialize, and you want the different specialized things to be able to interact with each other and learn from each other. And if you follow that line of thinking in a while, you'll wind up with something vaguely OpenCog-like, because you want a common representation for different specialized pattern recognition modules to be able to communicate with each other and interact together. And you also want specialization for different things so that you can do each thing reasonably efficiently. On the other hand, you also want the different specialized things to be able to learn from each other and communicate with each other. Now, of course, that's a very fudgy argument, and it's not rigorous, and you can posit a lot of different and complementary perspectives. But it is a coherent train of thought that leads you from an original, very simple and grand-sounding conceptual point of view to a big, nasty, complicated mess. And of course, the fact that the human brain is a big, nasty, complicated mess is at least a weak piece of evidence in favor of that hypothesis. So I gave a presentation at a conference in Singapore recently, which was sort of along these same lines, but a little more rigorous. So I'm gonna, if I can find it, go through that now, which will. These two. Yeah, I'm not going to go through all this in detail, but I want to talk a bit about first, as a preliminary to the other presentation, a bit about what is general intelligence, and I know all the variables in these definitions aren't even defined here, so you want to understand it. The little jog my own thinking here. This was a paper from the AGI-13 conference, where I tried to give a mathematical definition of what is general intelligence. And my starting point was a definition of Shane Legg and Marcus Hutter, where they defined general intelligence as, in essence, the average over all possible computable worlds of the ability to achieve computable rewards in that world. So, average over every world of every goal, how well can you achieve that goal based on interacting with the world? Now, of course, you have to weight that average somehow, and they weighted it by computational complexity. So you say, okay, we will average over all possible worlds and all goals. How well can you achieve that goal in that world? But the worlds that are simpler, in the sense of being computable by a smaller computer program, will be weighted more highly. So it's, if you can achieve simple goals in simple worlds, that's more important. And then achieving a complex goal in a complex world is proportionally less important. So that is the universal intelligence as defined by Shane Legg and Marcus Hutter. Now, Of course, by that criterion, humans are really, really dumb. Like we're really bad at achieving arbitrary computable goals in arbitrary computable worlds. We can barely handle achieving our boring everyday human goals in our everyday lives without fucking ourselves up somehow. But it's a reasonable grand definition of intelligence. Now I kind of played with our definition a little bit. I introduced a biased universal intelligence where if you have some given distribution, probability distribution over the possible worlds and goals, say a bias toward life on the planet Earth as opposed to in the center of a neutron star or something, relative to that distribution, you can say how intelligent are you relative to a certain distribution. And I think that's a little more relevant because we evolved relative to some particular set of goals and environments. And that's how we really evaluate our own intelligence. So I call that the pragmatic general intelligence. It's basically a weighted average of intelligence where you have a prior distribution given over environments and a prior distribution given over goals. And that is no longer a universal kind of intelligence. But then comes another sort of philosophical point, is do you count something as intelligent independent of how much resources it uses? Or if someone uses, say, all the energy of a whole galaxy to solve an IQ test, and some other guy solves the same IQ test using a MacBook Pro, do you say the MacBook Pro is smarter than the Galaxy because it used less resources? And that's really just a question of how do you want to chop up the definition. So I define the efficient pragmatic general intelligence is basically normalized by computational cost. So it's like how, given a certain probability distribution over goals and environments, how well can you achieve those goals and those environments on average? Normalized by how much resources you spend on it, which you can measure resources however you want. You can use space or time complexity or energy if you have a physics model or something. Now, this still isn't a perfect definition of intelligence. The problem with it is that the idea of goals kind of sucks. I mean, humans are goal-achieving entities only in a very limited sense. I mean, we try to, or some of us try to, orient our minds toward achieving goals in much of our time. But to say that we're fundamentally goal-seeking organisms is a fairly broad abstraction. I mean, you can say that in evolution, we evolved to propagate our DNA or something, but it's at best a partial explanation of what we do. And to explain suicide bombers and so forth, you need to invoke a lot of special argumentation. So what I came down to is the conclusion that yes, it's a dodgy approximation to say that we're trying to achieve goals as organisms. However, if you're talking about intelligence, that really is a quantity that it is relative to goal achievement. So if you want to give up modeling organisms as goal achievers, that's okay, but you're giving up measuring their intelligence too. So if you have an organism and you infer that that organism is trying to maximize certain goals, then indeed you can measure its intelligence relative to those goals. If you choose not to model the organism as a goal achiever, that's fine. Just give up modeling its intelligence. I think intelligence is tied to the optimization framework. And it may be that we should just be thinking about like synthetic, complex, adaptive systems rather than about general intelligences at all, right? I mean, that's what it is. These are building systems that adapt to the world and they're very complex. And so if you just want to think about synthetic, complex, adaptive systems, that's interesting enough in itself. Then you don't have to hack around about, well, what is this guy optimizing? What is the goal of this system? But insofar as intelligence is interesting to think about, and I think it's moderately interesting to think about, then you're stuck with identifying what are the goals of this system. And a big problem with this sort of abstract approach to defining and measuring general intelligence is that it kind of has nothing to do with building real AI systems at all, which is why I'm giving it now as a kind of afterthought. And the problem is that the environment is not formalized in real life. Like, we don't have a good formal model of this world that we live in. But what we really care about is making a system that is intelligent in this world that we live in. So unless you have formalized, like, what is the probability distribution over all computable environments that we care about, right? Until you have formalized the everyday world, what use is all this? It's only useful as conceptual inspiration, really. I mean, in a way, physics formalizes the world, but yet our AI system does not have to be good at achieving goals in all environments conceivable by the laws of physics. So what constitutes the human everyday world as a special case of all systems realizable from the standard model plus general relativity? I mean, who knows? Right? We can't even derive the periodic table of elements from physics yet without a bunch of hacking. So in reality, I came to the conclusion that mathematical formalization of intelligence, valid or not, is not going to be that helpful. No. It could be an interesting direction for research. So the question becomes, how do you build a bridge between IQ tests on the one hand and intelligence as the average capability to achieve goals and environments on the other hand, right? Clearly there's a bridge there. What we have found is that for certain kinds of systems, a measure of how well that system can achieve difficult goals in environments relative to us. A decent indicator of that is these IQ tests. And in theory, there could be some mathematical theorem saying why that's true. Like, for a certain distribution over environments and a certain distribution over goals, and a system satisfying these architectural constraints, the general intelligence, the ability to achieve goals and environments, is roughly proportional to the ability to do these specific things, which would be the IQ test, right? And that would be a very nice kind of theorem. I can imagine proving that kind of theorem in some toy cases. I don't know how to do it for general intelligences of a human-like character, and I kind of decided that that's a cool area of research that would take years or decades to figure out, and it would be a large distraction from actually building AGI, so I stopped thinking about it too much. But in a related vein, I started thinking about what would a good general theory of general intelligence really be like. And so far, this train of thought has not yet converged in any useful way with my practical work on OpenCog. My hope is they will converge in advance in the future. I mean, I think in the context of an AGI Summer School, this sort of thinking certainly has its place, because we're not here just to talk about system engineering, but what AGI is a valid topic. But how useful is this general thinking about general intelligence for actually building AGI systems? I'm actually not sure. I mean, I like math and philosophy much better than I like system engineering personally, so I wish you could just derive the AGI design from abstract thinking instead of having to tinker and engineer so much, but that didn't seem to be working, so I just set about tinkering and engineering. And that if you look in the history of science, often it happens that first people build stuff and tinker with stuff and get stuff to work, and the nice theory comes afterwards. Kind of partly induced from experience, and then like first you have a bunch of experimentation and tinkering and doing stuff. Then you have a bunch of bad special case overfit theories to various special things people have done and observed. Then finally you have some great synthetic theory that brings a lot of things together. So it might be that AGI will be like that, or it might be that this just isn't the sort of thing where there is a grand unifying theory. I don't know. So the idea here is to answer the question, like two symmetric questions really. What kind of world do you need to build a mind? And what, if you want to get human-like general intelligence, what kind of world do you need to foster its development? On the other hand, if you have a specific world, what kind of mind would you need in order to really be intelligent in that world? So this is my fantasy for a science of AGI, which is nowhere near remotely achieved yet. So you have the properties of some world, you feed that into this future science, and it will tell you what kinds of minds are capable of general intelligence in that world. On the other hand, you can give the properties of a mind, feed it to the science, it'll tell you what properties of a world would guarantee that that mind was intelligent in the world. And I think that kind of theory should be achievable, but we certainly don't have it yet. And this comes out of the idea that truly general intelligence in every possible world is achievable only with infinite computing power. So any finite mind is, whether explicitly or implicitly, biased toward a certain class of worlds. Yeah.
It seems to me that what you want there, for the top part, you simply specify that the world is a useful search space or search. You can structure the world as a tree, which can be searched to find goals at the leaves of the tree. And what the bottom half is saying is that you've got an AGI which can navigate that tree in a useful, computationally possible fashion. And then down the time or something.
You could model it as a tree. I wound up modeling it as a probabilistic state transition graph rather than a tree, but it's sort of a similar idea, I think. Yeah. But however you model it, we don't have any way to solve these problems yet either. I mean, if you have a huge search tree with certain properties, we don't have a general way to say what kind of mind can successfully traverse that tree based on the properties of the tree. And in some very special cases, you probably can. I mean, what we do now, basically we have some world environment or situation, and we kind of guess what kind of system will be good there. Or if you have some AI system, you figure out what problems to apply it to by intuition and then trial and error. That's how I'm proceeding with OpenCog, like everyone else is proceeding. So, and yeah, what comes out of this, what this comes out of partly is the hypothesis that human-like AGI largely reflects an adaptation to our everyday world. And on this level, I agree with Pei Wang considerably. I mean, he views intelligence as basically adaptation to experience and environment, and I think that is largely right. I mean, we are what we are because we adapted to the social and physical environment that we came out of. I mean, I wrote a paper once exploring what would a mind be like in like a fluid world, a water or gas world. Would it have the same notion of causality as we do? Would it have a language that break things up into discrete chunks like we do? Or do we think in terms of cause and discrete chunks of words, numbers, phrases, and so forth, just because we live in a physical environment where we tend to have discrete objects interacting with each other? I mean, we don't even know to what extent we are adapted to the realm of matter that we exist in. And of course, the same issue comes up when you think about environments for putting an AGI in. Like, does a preschool have the richness that you need for a human level AGI, or is it missing important things? Does a virtual world like the one Lake, Nicky, and Alex have built have what you need? I mean, we don't really know that because we don't know what are the critical properties. Like most game engines now deal well with solid objects and very badly with things like fluids and fabrics, right? Yet little kids really like playing with sticky things and liquids and all kinds of matter, right? How important is that? Is it cognitively important, or is it a nice to have? We don't have the answer to that question now. I mean, if you look into preschool, there's a lot of stuff there, right? And of course, before there were preschools, young children just followed their parents around, interacted in the everyday adult world with all its complexity. I mean, there's a lot of stuff in there, and if you think about what percentage of that stuff a contemporary robot can deal with without getting its joint gummed up, it's not that much, right? I mean, the robot's not going to play in the sandbox, it's not going to play with clay, it's not going to paint. It's not going to cook. It can't eat lunch, or it might pour milk into its joints. So, I mean, you could maybe make an analog for robots that had stuff that is friendly to the robot's particular body. Right? It's a lot of complexity. And if you look at current game worlds, they're pretty empty. Like, I mean, ours is a little fuller because of the block space modality, but the richness and diversity still isn't much compared to the environments that we want to put human children into. But we're gradually getting there. I mean, I think our current game world is better than our previous attempts, and we can improve it more and more. So, I mean, object-to-object interactions are simplified. Like you have a socket in the hand to connect with a socket on the eraser to pick it up, which means that you can't pick it up in all sorts of different strange ways, and learn from the different interactions you can have in picking the thing up, which is a limitation of the way the game engines are built for sake of efficiency. We were talking earlier about the problem of movement using canned animations versus movement using the inverse kinematics and the joints of the skeleton, which are all problems that can be solved within current game world architectures. They just involve more programming and less use of existing software libraries. Ultimately, you'd like to integrate a good robot simulator with a game engine or a virtual world engine. And you could do that in the Unity framework we're working with now. It's just a bunch of work to integrate the robot simulator with the game engine. Yeah, we don't have the naive physics of everyday life. I mean, you can simulate it in various ways, but it's the amount that a little kid learns just from seeing liquid poured in different vessels. You learn a bunch of lessons there that are kind of hard to learn in a game world composed only of solid objects. I mean, you can always get at the same lesson in multiple ways, but then there's the question of some things that are presented to human children every day may be hard to come by in a game world, and how much does that matter? I thought about how to design a game world where everything is made of little tiny balls and different laws for their interactions. It's kind of the next step beyond the blocks world. But again, oh. I forgot that was a video. Yeah. Of course, robots are supposed to be the solution, but like this was our robot playroom in 2009 in Xiamen University with the Now robot connected to some simple image processing and language processing software. But, you know, this robot world is not richer than the game world, right? It's like you put in only a few objects so the robot won't fall down or get confused. And what you end up doing is making a robot environment that is just as denuded of complexity and interest as a simple game world, and even more so, actually. I mean, our current game worlds are much better than that. I mean, robot soccer is also a highly simplified environment. Oh, there. All right, so it understands Chen Shuo telling it to go to the ball. the current now robot actually walks a lot better than the legs have advanced a lot in the last 4 years. But it is able to recognize where everything is, put it in its own app, and we just use IBM's speech-to-text technology feeding to some of the language software that Ray Tate will talk about this afternoon.
You mentioned a robot army of those?
Yeah, that would just be sad to watch them get shot down by a human army. That would be poignant.
The uprising has begun.
Yeah, well then 10 years later you see the super robots come in and mow down all the humans, I guess. Yeah, so merely using a robot doesn't really do it. I mean, if you're going to use robots, that's great, but you want to be putting the robots in a complex environment that has richness of detail visually and richness of motoric affordances. So one hypothesis I have is that these different kinds of knowledge, like declarative knowledge of facts and beliefs, procedural knowledge of how to do things, episodic knowledge of different agents' life history, sensory motor knowledge of what you see and what you can do, knowledge about what's important in what context and what goals other agents are trying to achieve. All these kinds of knowledge are important, and one thing to think about when you think about a world is, does the world support all these different things? Because certainly at a minimum level the human mind deals with all these kinds of knowledge. And most ways that we teach AIs don't support episodic knowledge very well, because we tend to run an AI for half an hour and then say, okay, our experiment's done, let's record the data and write a paper. But of course, being a child is all about episodic knowledge. It's all about lifelong learning and learning from your life history. And of course, in the simplistic environments that we create for our AI systems, knowing what to pay attention to doesn't come up very often either. But if there's almost nothing there, what to pay attention to is not a big problem. Yet, in the real world, it is a big problem, and it's something that human beings struggle with through their lives, is what to pay attention to. And we're not bad at figuring out what to pay attention to in our physical environment. But in a broader context, attention allocation is always hard for people. And we tend to solve that problem for our AIs by giving them simplified environments, mostly containing just what they need to solve their particular problem. So, in this paper, I went to some work to formalize a hypothesis that basically, if you model both the mind and the world as kind of probabilistic state transition graphs, so the mind has a set of states, the world has a set of states, and there's a probability of transition from one state to another. Then you can talk about a sequence of world states and a sequence of mind states. If a sequence of world states that can be decomposed into two parts can be nicely mapped into a sequence of mind states that's composed into two parts, then you have a nice mapping between the mind and the world. And my hypothesis was that if a mind is going to work intelligently towards certain goals in a certain world, then the sequences of world states that are relevant to its goals should have this property, that the decomposition of world state sequences into parts is mapped into a decomposition of mind state sequences into parts. And then I went through some work to formalize that, which I probably won't go into in too much detail here, because it's just a bunch of math. But I don't know, how many people are familiar with category theory? All right, since that's nobody, I definitely won't go into it. But that is probably the most abstract branch of mathematics, which has been used to provide a common formalization for every part of math. So set theory is one approach to formalizing math, and category theory is an alternative, which abstracts things a bit more. But anyway, in this paper I used the branch of math called category theory, and you can formalize the set of, if you have a graph with nodes and links, you can formalize a set of pathways through that graph as what's called a category. So I looked at the category of paths through the world state transition graph, the category of paths through the mind state transition graph. Then category theory has a notion of a smooth mapping, which is called a morphism. So I looked at smooth mappings between the mind state graph and then the world state graph. And my hypothesis was you have to have a smooth mapping like that in order for the mind to be intelligent in the world. But unfortunately, all I did was to formalize that hypothesis and did not prove it. But yeah, one nice thing about category theory is you get cool looking graphs to look at if you ever want to study it. Actually, in terms of programming, if you're into functional programming like Haskell or languages like that, category theory is used to formalize the semantics of those programming languages. So it pops up there as well as in advanced mathematics. But that, it was a lot of work just to formalize that hypothesis, and I decided, well, to prove that theorem is going to take me like 6 months of mathematics work. So do I do that, or do I work on OpenCog? I decided the hell with proving the theorem, and let's push ahead with OpenCog. But I think eventually, along lines somewhat like this, you will be able to get a mathematical theory that tells you, given an environment with these properties, this is the kind of AI system that could be intelligent in this environment. The problem with making that useful in real life is formalizing the environment, really, because the everyday environment is not a formal system. And I mean, if you abstract the environment in some very specific way, you might lose the richness and complexity of the real world somehow.
The environment includes human interaction, right?
Also, yes.
How to format that?
Well, we already know how. It's the standard model plus general relativity. You're all a bunch of little particles. It's just a big set of equations. And the problem being that those two physics theories are inconsistent with each other. So it's not really a good formalization. Yeah, I mean, I'm kind of undecided how important like general theory of intelligence is for building AGI systems. I mean, it would be nice if there was a general theory of AI that you could use to derive your AGI design, right? I mean, that would be beautiful. No. I mean, that's not how things generally work in other areas of engineering. Like, if you look at flight, which is always a ready metaphor for AI, like, we didn't derive the equations of aerodynamics and then derive the design for airplanes and helicopters from those equations. I mean, it didn't work that way. Like, rather, people hacked together airplanes and helicopters. You know, the ancient Chinese drew pictures of helicopters in 1200 or something, and then Leonardo da Vinci had those pictures, and people tried to build these things, and eventually they built the ones that worked. And then, around the same time, the theory of aerodynamics came about, which can then be used to make better and better airplanes and helicopters. So I kind of feel like it's going to go that way. Like, we're going to hack together AGI systems that basically work. The theory will develop concurrently, and then the theory will be used to make them smarter and smarter, to figure out how to improve different components to make them better, rather than it being so top-down, like you get some general theory and derive the design from that. But who knows that? Actually, it's all up for grabs at this point. So yeah, the overall message from this morning's excursion into theory is, at the philosophy level, intelligence may not be that complicated. Like sure, it's just about recognizing patterns in yourself and your world, recognizing patterns regarding which actions will achieve which goals, including self-modifying actions. And it's all kind of simple and makes sense. I mean, there's a whole problem of qualia and what is conscious experience, but I'll set that aside for now. On a functional level, intelligence is not that hard until you run into the problem that general pattern recognition would require a computer bigger than the entire universe. And then pattern recognition has to be specialized somewhat to a particular collection of goals and environments. And even then, it's really hard to do within the resources available. So you get into making many specialized things, and then connecting the many specialized things, and then it all gets really complicated, right? But you can kind of trace out the path from the simple version that doesn't care about resources to the complex version that does. So that the whole problem with complexity of intelligence comes down to not having infinite resources to be able to do truly general intelligence. So we need to bias and specialize in some way, which comes down to it sucks not to be gods. Right?
Terminological problem. Previously we talked about mana structure. Use the term module. Module is also used by philosophers.
It's used by mathematicians too.
Yeah, it's so little.
It's a common word.
It's too common, so it makes terminological confusion. In philosophy mind, Jerry Fodor, like Peter Tarsus, in module, they have a special module should have this kind of special feature of philosophical problem. The one module cannot intervene.
Yeah, then there are no modules in OpenCog or LiDAR or hardly any of these architectures in that strong sense. I mean, I think that we don't have totally encapsulated modules of mind in any of these systems. I mean, I think it's in most of these systems with multiple components, we take for granted that the components can interact with each other while they're doing their business. But yet on a software engineering level, they still may be separate bodies of code within your code base that still communicate with each other. Yeah, I guess the strong modular hypothesis no one believes anymore. Well, maybe Jerry Fodor still does, but he's an old man.
He had crazy conclusions that computational theory of mind in the global sense. He has a law.
Yeah, he has many strange ideas.
Yeah, the conclusion of strange.
So any comments or thoughts about any of these things? Or anything else relevant?
No, the big question is, yes, we can understand that OpenCog system, different modules can cooperate with each other where to do the job, to do the given job. But then where there's no variety, it will figure out a very challenging.
Where does novelty come from? Well,
Random number generator.
yeah, and the environment, of course, perceptions. In a very practical sense, Moses is an evolutionary learning algorithm, which generates a lot of random shit. So that's the absence of random nonsense is not a practical problem. I mean, philosophically, you got random number generators, and then you've got sensory input, right? But yeah, the evolutionary algorithm is good for generating apparent novelty. The problem is filtering through the novelty to find things that aren't crap. But I mean, actually, the attention allocation, which is all this kind of nonlinear activation spreading of importance, it is good at finding novel connections and attractors. And then if that is being used to guide inference as your inference control mechanism, that means you may have novel directions for inference as well. But I mean, in practice, lack of a lot of weird random stuff happening is not a problem. Lots of weird random stuff happens. So the problem is kind of getting that balance where you have weird random stuff that is semi-related to what you want to do, right? Having a lot of novelty, that kind of comes there from having so much stochastic stuff inside the algorithms.
I'm thinking that when you model the world and human intelligence, they are kind of two separate processes. But I'm wondering whether the reason that human or AI, an AI system cannot adapt to the world as human does is because the world and intelligence, they are inseparable. Because the human, like from the evolution, human evolved with the world. The
Yeah.
world is changing all the time. So if we model the world first and then try to develop the intelligence, you're making an assumption that the world is not changed. It's not going to change. So our knowledge of the world is deterministic. So it's not going to change.
I think that there's some good points there, but I don't think we're assuming a model of the world in which the world doesn't change necessarily. I mean, if you look at the world as a kind of probabilistic state transition graph or something, there's a lot of uncertainty in there. So the world certainly could change, but it is a valid point that, I mean, we are part of the world, right? We evolved within the world, and then there's the kind of extended mind hypothesis, which has been put forth in cognitive science, that you don't even want to think about the mind as just in the brain or the body. Like your mind includes tools that you use, people that you interact with, and your whole. I mean, Andy Clark has been the most famous one for bringing this forth in philosophy of mind, but many others have talked about it too. So I mean, the idea that your mind is extended beyond your brain and body anyway. And that if you take that into account, things start to look a bit different. But I mean, if you just go back to systems theory, you always start with a kind of undifferentiated existence, and you draw the boundary distinguishing between the system and the environment. And
Almost six.
yeah, almost six. I'm not going to project anymore. I mean, you draw the boundary between system and environment as an act based on an agent analyzing the world in order to understand something. And I mean, it is useful to do that because otherwise you can't say anything. I mean, it's not necessarily absolute where you draw that boundary. You just have to draw it somewhere in order to make an analysis. And I mean, otherwise, all we can say is there's this one big complex adaptive system, which is great. But if you want to talk about intelligence, that is intelligence of some separated agent interacting with the world. And you kind of need to distinguish the agent to talk about intelligence at all. But it's not always obvious where to draw the boundary. Like, and if you think about like how much of your intelligence is you and how much is culture, like human culture, right? I mean, it's most of it is the collective mind of humanity and not the individual anyway. And you can analyze it on that level as well.
Do you feel like you could really just draw that line kind of anywhere for the first iteration or something?
No, some places make less sense. Like drawing the line like the top half of my brain, or me plus Fidel Castro. Those are stupid ways to draw the boundary, right? Whereas drawing it around my body or my brain or my body and things I interact with is not that stupid. It makes some sense. I don't think it's arbitrary. I think some distinctions lead to interesting conclusions and then some don't, right? But but it's not totally arbitrary, but nor is it absolute.
So the process for selecting that is more of like a design problem than an engineering one, you'd say?
Well, it's a philosophy problem, right? I mean, I think the way to draw the boundary is the place which enables you to draw the most interesting conclusions. And then how do you know what's an interesting conclusion? I mean, that's like in philosophy of science, like Imre Lakatos' theory of research programs in science. Like, how do you ultimately distinguish one scientific theory is better than another? Because each one kind of gives an incremental view of the world compared to the other ones. And what constitutes a valid experiment is itself part of the scientific theory. So then there's not, in the end, an objective way to compare one scientific theory to another, because they may not even agree on what is real or what is a valid experiment, what constitutes evidence. So ultimately we distinguish scientific theories by which ones are more progressive or regressive. Like if some scientific theory seems to be generating interesting and dramatic new conclusions, then people will jump on board with that. If some scientific theory seems stagnant and not to generate anything new or interesting, you get bored with it. So it's sort of the Hollywood movie theory of scientific value. But I think that the same thing holds here. If we learn something new from drawing the boundary around your extended mind rather than just your brain, then that's enough, basically. We're getting very philosophical here.
Maybe I can ask a low-level question as well. What do you think of multi-agent method? Because I think in principle, it sounds very nice that each agent observes the world as a world that consists of multiple agents, and they can all act.
So I'm not impressed by the progress in the field of multi-agent systems. On the other hand, I don't want to be too high-handed about that, because I could easily say someone saying they're not very impressed by the progress in the field of AGI, and I couldn't really argue with them. The practical progress hasn't been great in AGI either, even though I think we have good ideas and are poised to make great progress. So I think that it's going to be good to have multiple AGI agents interacting with each other in a common world. I mean, it's going to be a valuable thing to have. And in designing an AGI, you want to take into account how the AGI will model the minds of the other agents around it and so forth. Ultimately, I still think the hard part is designing the individual mind, at least if you're doing anything remotely like a human, like AI system. So yeah, I think it's going to be valuable to take multiple complex AGI systems and have them interact in an environment, like multiple game characters in the game world or something. Now, can you achieve the individual mind itself by thinking of the mind as a sort of society of mind, a la Marvin Minsky? I kind of doubt that. I think, say, a human mind is a lot more structured than a society. I mean, the different parts of the brain do specific things, and the brain architecture has a lot of specific order to it, much more so than the human society does. So I'm not that bullish on the multi-agent system, society of mind type approach as a paradigm for creating the individual mind. I mean, in a broad enough sense, I mean, OpenCog is a multi-agent system. We have mind-agent components that act on the atom space, but that would be one criticism of the whole agents field, is what is an agent? Everything is an agent, right? So I mean, if you want to interpret it broadly enough, any software program is a multi-agent system. I mean, object-oriented programming, you have these multiple objects, they're encapsulated, they interact with each other. So, but generalizing it that far probably isn't useful either. I do think, like, if you look at Stan Franklin, he wrote a paper like 4 pages long. Is it an agent or is it a program? Which he's always laughing because that program is cited like 100 times more than any of his other papers. Although it's a quite trivial point, whereas he's actually done some things with more depth to them. But everyone, whenever they mention agent, they cite that paper. Right? So, yeah, is it an agent or a program? So, I mean, his point was that a program takes inputs and gives outputs. An agent chooses actions based on its sensing of its environment. And that's sort of a different thing. And I think it is important to think of AGI systems as agents and not just programs in that sense.
So the question is your idea of modeling the world an extended version of highest naive physics?
Well, naive physics is very interesting. I mean, I've certainly, I've read that stuff and I liked it. It's not very well formalized either, though. I mean, that's more of a conceptual theory. But yeah, I think that will be part of it. Then you have folk psychology, which was another aspect. So yeah, I think that's naive physics is a sort of classic line of thinking of AI going back decades, where they try to model like everyday physical reality, like make a theory of rough edges, a theory of fuzziness in the sense of like the fuzziness on the human or animal, not fuzzy set theory, right? Make a theory of stickiness. So try to theoretically sort of formalize all these different aspects of the everyday world that we live in, which includes concepts that have nothing to do with particles and electromagnetic fields and all this lower level stuff. And yeah, I think that was an interesting idea. I mean, it highlighted a lot of things. Like the main concept they came up with in naive physics was that of a boundary, like the boundary between one object and another, one type of texture and another. So you wind up thinking of the world as a set of boundaries of different types, nested within and overlapping each other. Interesting line of thinking. I mean, as with everything else, when you try to formalize something natural, you can get like 80% of the way there pretty easily. Then as you want to get more and more coverage of reality, it gets more and more complicated. Kind of like with grammar rules. Like you can articulate some grammar rules fairly simply to cover 80% of simple sentences. And if you want to cover all sentences with grammar rules, you can add more and more horribly complex rules, and you never quite actually get there in real life. And naive physics, not nearly as much effort went into that as into formalizing grammar. But I think ultimately it's the same kind of thing. You can say a lot about a lot of everyday physical situations without that much complexity. But if you really want to cover everything a human level AI would need to do, you couldn't do it by formalizing things. But if your goal isn't to formalize stuff to guide the AI, but just to formalize the everyday world in order to do theory and prove theorems about the relation between the world and the mind, in that case, it's like a formalization of some extended naive physics could be quite interesting. Sure. Not many people have been working on that recently. And in principle, you could induce something like that by applying pattern recognition to the output of a robot and video cameras and so on experiencing the world, right? Like imagine you took every YouTube video right now. There's all kinds of fluids and pastes and fabrics and so on there. So in theory, by inductive reasoning from all those videos, you could induce a naive physics. But that would take an AGI system in itself to perform that induction. So it might be that the AGI is what will build the formalization of the world. Because once you have an AGI that interacts with the whole world, you could then analyze the structures in its own mind. And that would give you the formalization of the world, which you could then use to prove theorems about that AI. If you had an AI like a NARS or an OpenCog, which had a knowledge base that was reasonably comprehensible in formal terms in a way. Like, to interact in the world, the NARS system would have to have learned a formal theory of the world inside its mind, right?
But such kind of model from your mind should be different from originated from another.
Not clear. I'm not sure. If you had a NARS system and an OpenCog system,
Maybe
yeah, I think ultimately their theory of stickiness is going to be about the same. Just like, I mean, you know, you and I had very different life experience, right? Very different view of the world. But if you could look at our brains and get our theory of, you know, peanut butter, jelly, butter, mustard, and how these different sticky substances interact, it's probably about the same theory. I mean, we probably have about the same common sense about these things, actually. I mean, just like grammar, just like language, right? We probably have about the same theory of how prepositions interact with verbs. We both learned it independently. And there might be some cases where we have a different theory, and those differences could be interesting. I mean, that could be how language evolves from these subtle differences, but it's about the same theory, I guess.
So you mean we can study physics from a new perspective, right? Different systems to learn the physical world,
Yeah.
and then find the combinations. Yeah. So we do not take care to it.
Yeah, exactly. Right. That's probably how it's going to happen. Because there's a lot more people working on building AIs than working on formalizing naive physics. I mean, grammar the same way, right? If you had a system that could really learn language, like when OpenCog really learned language, you could then mine from its knowledge base the rules of grammar at a much finer level than humans are able to encode them. Actually, some of the work Ray Ting is doing now is aimed in that direction. Just statistical mining of grammar rules. Now, computational linguistics now has so many simplifications, it hasn't really been useful for that purpose. And the grammar rules that computational linguistics systems learn don't really go beyond what people have coded by hand. But if you had an AGI that really learned language fully, I guess it would be able to. Yeah. And then maybe once we get that formalization of the world from the first generation of AGI systems, and maybe people can use that to design much better and more elegant AGI systems afterwards. I'd be surprised if not. I mean, whatever AGI system gets there initially, we'll look back on that like the Wright brothers aircraft or the Model T car or something, right? It's going to look incredibly archaic and bad compared to the systems that come later after we understand what we're doing. Anyone else?
Are institutes like the Santa Fe Institute for Complex Systems thinking about AGI?
No.
Shouldn't they?
Well, asking me normative questions is complicated. The whole world should be very different than it is, but that's kind of beside the point. I mean, historically, the Santa Fe Institute didn't have any AI guys, and they're kind of founding cabal, and they just have tended not to go in that direction. I mean, what they're doing is interesting, and they have limited resources. So, I mean,
when they give examples of complex systems, they do tend to include intelligent brain-like things.
Yeah, they like neuroscience. They just don't like AI. I mean, yeah, that would be something that the connection between the complex systems community and the AI community is fairly weak, which is a shame, because I think there's a lot of cross-pollination you could have there. I think that came about because in the 70s and 80s, the US AI community went so far in the direction of kind of rule-based and logic-based AI. And that's the same time that the complex systems community emerged more from the chaos theory and dynamical systems community. So at the ancestral time for both of these fields, they were totally different from each other. Now both of them have evolved a bit, and you can see on the technical level the basis for cross-pollination, like symbolic dynamics. You know what that is, for example? Symbolic dynamics is the use of symbolic systems to model complex nonlinear system. So you take the state space of a complex system, the space of all its possible states, you divide it into a set of discrete intervals, discrete bins, and then you model the sequence of states of that system as the sequence of discrete symbols from some alphabet. And you can look at like what formal grammar is implicit in the dynamics of a system. So when a system approaches chaos, the formal grammar implicit in the sequence of its states gets to be a more and more complex grammar, going from like a context-free grammar to a context-sensitive grammar to a more complex phrase structure grammar. So the grammar of states of a system gets more and more complex as it approaches chaos. So, but you could certainly hybridize that sort of work with work in symbolic AI, but yeah, nobody's doing it. So when you become a billionaire and found the Cosmo Harrigan Institute, then you can fund that research. All right, I think it's lunchtime. So after lunch, we can have a bit more with the game world, I guess, and then Ray Ting will take probably 45 minutes or something, and then go over OpenCog's natural language processing, and then we can have some interesting discussions on how that should be done and how it is being done, and so forth.